Okay, in this presentation we are going to look at the negative binomial distribution. So reading the question, the probability of a male birth, the probability of giving birth to a boy, is, let's say, 50%, 0.5. Okay? A couple wishes to have children until they have exactly 2 female children in their family. Okay? So, a couple of questions. Write down the probability distribution of X, the number of male children before there are 2 female children before 2 girls. Okay? Then, what is the probability that the family will have 4 children? What is the probability that the family will have at most 4 children? What is the expected number of male children this family will have? And what is the expected number of children this family would have? Okay. So, we're going to use the negative binomial distribution for this. Okay, so where X is the number of failures given R successes, the probability mass function of the negative binomial distribution is given as follows. Okay, it's probability X equal to K, where K is the number of failures before we have R successes, given a probability of success. Now, a little bit sort of jarring to think that, a failure would be giving birth to a male child and a success would be giving birth to a female child, a girl. But that's the terminology we would use with Bernoulli trials. So we'll just go along with it, okay? So this is the probability mass function, which looks for the number of failures before R successes. So X is the number of failures before the prerequisite number of successes, which is R. So the probability X equal to K, which is some particular number of failures, that is this term here, or 3 terms. So first off, we have the binomial coefficient of K plus R minus 1 and R minus 1. So there's a little bit of work involved in that. The other 2 terms are straightforward enough. 1 minus P to the power of K times P to the power of R. So where R is the number of successes, K is the number of failures, and P is the probability of a success. And again, we're dealing with in the context of Bernoulli trials, where an experiment can have 2 outcomes. One, we denote the success, and one, we denote the failure. Now, just something actually I'll remark upon here before we continue is that you will actually find, as you get more familiar with the binomial or the negative binomial distribution, is that there are actually quite a lot of ways of specifying the negative binomial distribution. Now, just actually draw your attention to the fact that we have 1 minus P to the power of K here, where K is the number of successes we are interested in, times P to the power of R. Now, you also will actually deal with several different varieties of the binomial coefficient as well. Now, just to highlight the point that there are actually multiple specifications of the negative binomial distribution, and over the course of your studies, the course of your work with the negative binomial distribution, you should get very acquainted and very aware of these various different specifications and when and where to use them. So again, I highlight the fact that the failure probability, 1 minus P to the power of K, that would have the power of K, where P, the probability of success, has the power of R there, which is actually a constant in this distribution. So watch out for things like that, how it's constructed and which way it would be constructed. I just draw your attention to something slightly different, where X is the number of trials given R successes. So this is a slightly different question now. The number of trials given R successes. Okay, the probability mass function will be given as follows. Probability of X equal to N equals the binomial coefficient of N minus 1 and R minus 1 times P to the power of R times 1 minus P to the power of N minus R. Now you're probably thinking, actually, that's actually very close. They're actually very close to one another. Yes, they are. So it's essentially, we're not reinventing the wheel each time we do use a different specification of the negative binomial distribution, but the question here is actually slightly different. The total number of successes, the total number of trials, actually, I should say, in this second case, including the failures and the successes, where up in this first case, it's number of failures only. So just watch out for stuff like that. That's actually quite important when you're dealing with the negative binomial distribution. Okay? Now, this question is fairly straightforward. It does actually deal with the first case, so we'll use that from now on. But just, be careful about this going forward. So, solution. A couple wishes to have children until they have exactly 2 female children in their family. The birth of a female child is considered a success, and the birth of a male child is considered a failure, which is very tough going to here. But anyway, again, it's just Bernoulli trials and terminology. The probability of a male birth is 1 minus p, which is also known as q, also commonly known as q, and that is 0.5. And the probability of a female birth is also 0.5. Okay, so p is equal to 0.5. 1 minus p is also 0.5. So the number of successes we're interested in throughout this exercise is r equals 2. So that's going to stay constant the whole way through. So let x be the number of male children before there are 2 female children. So therefore, the random variable x follows a negative binomial distribution, which we would denote as follows: x nb r equals 2 and p equals 0.5. Something like that. You should always that should always come up some stage to actually write out something like that when you're dealing with a exam question that deals with random variables and probability distributions. Just a formal, semi-formal statement about what you're doing and what the terminology means. Okay. So, first question, the probability distribution of x, the number of male children before there are 2 female children. Using the first specification, r is equal to 2. X here is the number of male children, so the number of failures before r successes. So we're dealing consistently with 0.5, both as p and 1 minus p. So just watch out for that in future. So it's, in this case, it's a little bit hidden. So 0.5 to the power of 2 times 0.5 to the power of x. That's actually going to stay fairly consistent the whole way through from now on. That part there. So here we have the binomial coefficient. Here r is equal to 2. So x plus 2 minus 1. From that, choose x, which can be simplified as x plus 1, choose x. So the binomial coefficient of x plus 1 and x. Just as a quick remark, there are ways to sort of respecify binomial coefficients. Okay, just to make it as simplified as much as possible. So the way I have it sort of stated there, let's go back a bit, would be actually is equivalent to the way I have it stated up here, but you just rework it. Okay, so there's a lot of work you should do with binomial coefficients, and really you should do them before you get started with this. Actually, just really practice with them and so on. So that's essentially a very straightforward version of the probability distribution of x, the number of male children before there are 2 female children. Here the support, as they say, is the number of possible values of x. So that you could have 2 female children straight away. Okay, there could be 1 son, or there could be 2 sons before there are 2 female children. Now the ordering is not important. So in this, let's say in this case where there is 1 male child, that could be that the male child is the eldest or the middle child. Okay, and likewise, any combination where you can have 2 male sons before you have 2 daughters, you know, it could be the 2 older boys or a girl and then 2 boys and then the next girl. It doesn't matter. The order doesn't matter, okay? So, part B. The family has 4 children, meaning 2 female children and 2 male children. Thus, the probability of a family having 4 children is the same as the probability that the family has 2 male children before there are 2 female children, before there are 2 girls. Okay, so let's just check what the question was again. What is the probability that the family has 2 children? So that is to say that they have 2 sons before they have 2 daughters. Okay, so what we're interested in there is the probability of x equal to 2. So here what we do is work on our binomial coefficients. Okay, so again, this is 2 plus 1, choose 2. Okay, so that is from 3, choose 2. And you should work that out. It should be fairly straightforward to work that out. That actually works out to be 3. Okay, so that's what that will work out to be. 0.5 to the power of 2 times 0.5 to the power of 2. Working that out, it should be 0.1875. Now, the probability that the family has at most 4 children means that x is less than or equal to 2. So what we have to do is calculate the probability of no sons, 1 son, and 2 sons, okay? And add them all together. So the probability of x less than or equal to 2 is from 0 to 2, the probability of x equal to x. So essentially it's probability of no sons, no male children, one male child, and then two male children. Okay, I just paused it there for a second because really I should have made a formal statement about what the binomial coefficient was of x plus 1 and x. So it is x plus 1 factorial divided by x factorial times 1 factorial. Now the 1 factorial is essentially 1, so we're going to sort of disregard that the whole way through. So just put but it is there. So 0, 1 factorial, 1 factorial, and 1 factorial. We don't really need to pay that much attention to it, okay? But it is there. That's actually just for the sake of consistency. 0.5 squared will come up the whole way through as well. So that is going to be consistent. Here at the end we have 0.5 to the power of x, so it's 0.5 to the power of 0, 0.5 to the power of 1, and 0.5 to the power of 2. Okay, so fairly consistent the whole way through. So the probability of x equal to 0, that is 0 plus 1 factorial, which is simply 1. And 0 factorial is also 1, so that works out to be 1. Here we have 0.5 to the power of 0, that's 1. So all we end up with really is 0.5 squared, which is 0.25. Okay, so that's where we get that. And the second case, the probability of x equal to 1, so that's 1 plus 1 factorial divided by 1. So that's 2 factorial divided by 1, which is 2, essentially. So that's going to work out to be 2. 0.5 squared, okay, which is again consistent, times 0.5 to the power of 1. So that 0.5 and 2 are going to cancel out. So again, we are also left with 0.25. And again, probability of x equal to 2 is 2 plus 1 factorial divided by 2. That will work out to be 3 times 0.5 squared times 0.5 squared. That will work out again to be 0.1875. Okay, so you can just disregard that. So part D, the expected number of male children. Okay, now this is the formula for the expected number of the expected value of x. That is for the negative binomial distribution where we have x specified the way we have previously. And this is specific to that specification. If there are other specifications, there is an adjustment to the expected value formula accordingly, and likewise the variance. So just double check when you're using a particular specification of the normal or the negative binomial distribution that you are using the correct specification for the expected value and the variance also. So here it is r times p, which is r times 1 minus p, r times q actually, which is r times 1 minus p divided by p. And in both cases, r 1 minus p and p are 0.5, so it's straightforward enough. So essentially we're left with 2. R equal to 2. 2 times 0.5 divided by 0.5 is 2. So that is the expected number of male children that the family will have before they have the two daughters, the two female children that they require. So the expected number of children is, so if we are getting 2 sons, and that's a random variable, but we're planning to have 2 female daughters, so probably that's the expected number of children is the expected value of x plus 2, which is the expected value of x plus 2. 2 plus 2 is equal to 4. Okay, so that's it. We'll leave it there.